So now that we know how to find these solutions for homogeneous linear systems, let's look at non-homogeneous linear systems and how we find those. The methods we use is the same method we used for non-homogeneous linear equations. It's the method of variation of parameters. So x prime is equal to a times x plus some function f of t. You're going to first, just like we did before, find the solution to the associated homogeneous. Once you have that solution, and the solution would be C1x1 plus C2x2 all the way through, you get these wonderful little solutions. You get this nice little matrix you can make up with these. And you can think of these as multiplication, because that's really what it is. You've got some constants here times your x's here. And so you can pull those constants out and think of it as you've got a matrix here, a square matrix, times this column matrix. And you can think of this as you've got some phi of my matrix. We're going to call this matrix phi times your constant matrix here. Phi is known as your fundamental matrix. And phi prime times a times phi is a solution to the differential equation, so they work out nicely. We are going to assume that phi is what we call non-singular, which means it has a way to find the derivative of it, and not the derivative, but the determinant of it is not 0. So we are going to assume that that's the case. We're going to consider some differential equation here where we have non-homogeneous. The solution would be x equals the complementary solution plus the particular solution. The particular solution is that fundamental matrix times the integral of the inverse of the fundamental matrix. And that's why it can't be singular, because if it's singular, it doesn't have an inverse. We need it to have an inverse, and then times that function matrix dt. This is actually the formula we use. Technology will actually allow you to find this without having to do this all by hand. You can use technology to find this. The TI Inspire will do this for you if you needed to. All right, so let's go ahead and solve a system. We have this one here, x prime 2 negative 1 4 2 times x plus sine of 2t 2 cosine of 2t all times e to the 2t. The homogeneous would be x prime is equal to negative 1 4 2 times x. So again, the first thing we're going to do is solve this homogeneous equation. That means the very first thing we're doing is taking the determinant of a minus lambda I, and that will be the determinant of 2 minus lambda, negative 1, 4, 2 minus lambda, and that's going to equal 0. Well, the determinant of that, again, you can use technology if you want to, but the determinant of that is fairly easy to do. It's lambda squared minus 4 lambda plus 8 equals 0. So lambda is equal to 2 plus or minus 2i. Again, what we do when we have complex answers is our lambda is, we're going to use the 2 plus 2i. And then when we do that, we have 2 minus 2 plus 2i, negative 1, 4, and then 2 minus 2 plus 2i. So again, you're basically subtracting that eigenvalue off your diagonal times your k is equal to 0. Again, we'll call this one k1 because it could be another one. So when we do that, we're going to let k1 be the matrix. So this is negative 2i, negative 1, 4, and then negative 2i. K1 we'll call K1, K2. And that's going to equal 0, 0. that zero matrix. Again, the way matrices work is you can multiply these matrices together and then matrices equal by components. So we're going to have negative 2i times k1 minus k2 equals 0. 4k1 minus 2i k2 equals 0. Believe it or not, these are actually the exact same. This one tells me that k2 is equal to negative 2k1i. They actually work the same way. This one also is if you use idea of complex numbers. So again, pick something for k1. I personally would pick 1 for k1 because you can. There's no fractions. K2 would therefore be negative 2i. So k1 is the matrix 1, because that's a k1, and negative 2i for k2. Remember, that's really 1 plus 0i and 0 minus 2i. That really is what that is equal to. We let B1 be the real part of K. The real part is the 1 and the 0. So B1 is 1, 0. B2 is the imaginary part of K1. That's the I parts, but it's not the I, it's the coefficients of the I. The coefficients of the I are 0 in the first one and negative 2 in the second one. So it's 0, negative 2. So therefore my x1 is the real part, the B1, which is 1, 0, times the cosine of 2t, because remember my eigenvalue was 2 plus 2i. So my imaginary part is 2, so that's where that 2 came from. Minus 0, negative b, because remember it's b1, the cosine of at or beta t, minus the imaginary part, 0, negative 2, times the sine of beta t. And that's all times e to the alpha t. In this case, alpha was 2, because that's the real part of my eigenvalue. My x2 is switching these. So you start with the imaginary part times the cosine of 2t plus the real part 1, 0 times the sine of 2t e to the 2t. When we have imaginary eigenvalues, you would get the exact same answer if you use the 2 minus 2i. So we don't worry about using the conjugate one. So my x sub c is c1 times 1, 0 cosine of 2t minus, and I need another parenthesis here because that's c1 times all of it, minus 0, negative 2 sine of 2t plus c2 times 0, negative 2 cosine 2t plus 1, 0 sine of 2t. I'm running out of space and I need to put in my e to the 2t on the outside of all that. All right, that's what my x of c is equal to. I can therefore find out what my fundamental matrix is. So my fundamental matrix, phi is the symbol we use for that. You can use anything you want. It really doesn't matter. But phi is what most people use. That would be the, going back to this solution we just came up with. We don't include these c's. We don't include the c1 and c2. But we're going to have 1 times cosine of 2t, then minus 0 sine of 2t. So it's just going to be cosine 2t. And then you're going to have sine of 2t for the other one. And then you're going to have minus or plus sine 2t plus 2 sine 2t minus 2 cosine 2t. So just putting them in that order with your e to the 2t in there. So we have e to the 2t times cosine of 2t, e to the 2t times the sine of 2t, 2e to the 2t times the sine of 2t, and then minus 2e to the 2t cosine of 2t. That is your fundamental matrix. Your function matrix was sine of 2t times e to the 2t and 2 cosine 2t times e to the 2t. And if you want to pull that e to the 2t out, you can. And then all we have to do is find out what x sub p is. X sub p, again, is your fundamental matrix times the integral of your inverse of your fundamental matrix times f of t dt. So you would go find out what it is. Again, technology can do this. Finding inverses are not too bad. You can go through the process if you want to, or you can have technology do this for you. This isn't a class in learning how to do that by hand. Linear algebra is. But you get minus 1/2 e to the 2t sine of 2t and 0. So that means that my x is that sine of 2t, I'm sorry, cosine of 2t sine of 2t, 2 sine of 2t minus 2 cosine of 2t, all times e to the 2t times my C matrix plus this minus 1/2 e to the 2t sine of 2t 0. And that's my solution. So that's how we solve non-homogeneous. It is a bit of a computational nightmare in some ways, but if you're using technology, it's not too bad. Your calculator can actually do all this. I believe other technology can also.